But it's like half. It's half. It's huge. And then there's another one like
Yes, Jared? I mean, you can't be dead to me. So the correct phrasing would have been, I can't be dead to you.
Come on, Jared. Really?
Sorry, I'm kind of a grammar.
Let's go ahead and get started here, please. We are going to be taking a quiz on Wednesday over sections 1, 2, and 3. Okay, and we'll review. I mean, we'll finish up any new stuff really for the most part today. Tomorrow we'll kind of be going over those questions, kind of do some review problems. Probably spend a fair amount of time. There aren't really any good review problems in the book. At least at the summary at the end of the chapter. Most of the review problems there deal with sections 4 on to the end of the chapter. So talk about going back over some of the old homework problems, some of these worksheets and that kind of thing. But let's do one thing here first. Let's kind of summarize for the worksheet, and actually for the limit problems in the book. The emphasis on today's homework was no calculator. There's going to be 2 parts to the quiz. There's going to be a calculator part and a no calculator part. Today we'll spend a lot of time dealing with the calculators as well and showing you what I want you to be able to do there. But no calculator is a big part of it. And of course, if you have a graph like those ones in the book on 13 through 26, be able to look at graphs there and think about that video that we saw with the cars meeting. That's really what it's about. I mean, a limit, if 2 cars are coming in to the meet at the diner, so to speak, that's what the limit is. And somebody was asking me this morning about limit, what the answer. A limit is a number. So the answer to a limit problem is always a number, or the limit does not exist. And of course, if the limit does not exist, we have to go one step further and we have to say why it doesn't exist. Of course, the only reason a limit doesn't exist is if the cars don't meet. Right? That's the only reason a limit doesn't exist. The cars are either going to meet at one place, at one number, at one y value, and that's the limit, or the cars aren't going to meet. If the cars don't meet, the limit doesn't exist. Why didn't they meet? Well, what's the car on the left do? Where does it end up? Where does the car on the right end up? If they don't meet, they must end up at 2 different places. So if you ever say in a limit problem the limit does not exist, you have to then go on and say, okay, what's happening to the left of 1 and what's happening to the right of 1 or whatever the limit is approaching, and what number are they approaching there? Okay, so that's essentially what are the 2 possibilities of what can happen in a limit problem. Okay, now the types of limit problems that you run into and the things that happen as you go along the way could be broken down into a few other options. So let's take a look at that. So the first possibility, the first thing that can happen on a limit problem is you get something like limit as x approaches 2 of x squared plus 3, and you do what? What happens? You do direct substitution. You always use direct substitution first. All right, so you put a 2 in there. You get 2 squared plus 3, which is 7. That's the limit. Now, if you wanted to look at that graphically, you wouldn't have to. But if you want to look at that graphically, x squared plus 3, think about the problems you had in the book. X squared plus 3 would look like this. As x approaches 2, as the car on the left is coming towards 2 and the car on the right is coming towards 2, they both meet at 7. All right? This might not be a bad time to just get our calculators out, even though this is a no calculator problem, but I want you to be able to understand and see limits in all of its different forms. If you look on your calculator now, Well, I'll show you this first one just so everybody knows it's there. I guess it's a nice little check, but it really does you no good. You will get 0 points for being able to do this, okay? But it's kind of cool. If you go to either the menu and go under Calculus to number 4, which says Limit, I'm on the calculator screen now, it brings up this thing. Okay? That was under Limit. Now, the other option is to go to your template here next to the 9. Same place I showed you where derivative was. And it's not there. And so that's not another option. Isn't it? No.
It's the last right there.
Oh, there it is. Yes, it is there. There it is. It's the very last one. I was going to say it should be there. And so if you make that selection, it's right there. So that's in your templates next to the 9, or it's under the calculus menu. All right? And so what are we going to put? Well, for this problem, we would put x in 2. Now, what's that other little box for? For the left or the right, right? A negative for left. Now, I'll be honest. I don't know what to put here, so let's just experiment. Well, we wouldn't want to put anything for this one, right? For this problem, we wouldn't want to put anything. We can just leave it blank. But if we were doing, well, let's just leave it blank for now. We'll come back and experiment in a minute. And then in here, we would put x squared plus 3 and hit enter. Okay? Now, if I grab this, if I go up and grab this and bring it back down again, I'm not sure what I'd put in. If I just hit the plus sign, maybe? Makes sense. Okay? Which makes sense because the car from the right is approaching 7. And if I go ahead and go up and grab that one more time and change that plus to, I don't think you'd use the minus key. I think you'd want to use the negative. I might be wrong, but no. Use the negative key.
It changes.
Yeah, well, I don't, it made it longer, but I don't think that, you could try the subtract key. I'm not sure if that
It works. It works.
minus key, subtract key works. Okay, good. So the limit from the left, limit from the right are both 7. So you certainly can do that as a check. Now, I'll be honest with you. On the calculator part of the quiz, and same with our worksheet, we have a worksheet today where we're going to be using our calculators. The answer I don't really care about. Matter of fact, I think on the quiz, I'll give you the problem and tell you what the limit equals. I'll say the limit equals 7. The problem for you is to justify that the limit is actually 7. Show that the cars are meeting at 7. Okay? So, but this is nice to have, and this is nice to know and be able to do. Again, this is the CAS part of this calculator. Without the CAS, you wouldn't be able to do limits on this. Okay, go to the graph screen, please. Here's what we will be doing today with the calculator limit problem. Anytime the directions tell you, either on the quiz or the worksheet today, says evaluate the limit using your calculator, this is what I mean. Not what we just did, but to do this. So we would come in here and we would graph x squared plus 3. All right? And my directions, I usually say use a table or use a sketch or use a, to justify. I'll be real honest, the table's the best way to go. The table is the easiest way to get full credit and to justify that the limit is set. And the way we get a table is we go, I think it's in the menu, in the, oh shoot, geez, I just did it. It's in View, that's where it is. Under Menu, when you're in the graph screen, go to Menu and then View and then Show Table. Now you can also hit Control T. That says Command T. That might be a computer. Maybe Control T doesn't work. Let me back out of that. Yours says Control? Oh, good, because since I'm using the computer software, it says Command. Control T brings up the table. So that's a nice little shortcut to know. So when you're on a graph, when you're looking at a graph, hit Control T, and it'll bring up a table of values. All right. Now, we're going to have to do a few adjustments with the table. Because what we're interested in now, and again, the reason I like doing the table is because I think this really gets at the concept of what a limit is. The limit is saying as the x's are getting close to 2, the number we're looking for, what are the y's getting close to? So, of course, we can tell when x is a 2, we can tell y is 7. But remember, we don't care about that. The diner could be burned down. There might not be a number at 2. So we don't care about that. What we care about is what the values are getting close to. All right? So we need to go make a few adjustments in here. So if I go to my menu, okay, now that I'm in the table. Now, you got to be a little bit careful here. In the next couple days, I want you to really play around. You're going to have to on your worksheet with this table. If you're having trouble with it, let me know. So it's not an issue for you on the quiz. But notice, let me hit escape back out of this. Oops. Back to my scratch pad. Now, notice that my table is highlighted right now. Okay? If I click over here in the graph, now the graph is highlighted. See, I'm on a split screen. So if my graph is highlighted, if I go to menu, I get all the menu options. I want the table to be highlighted because I want to work with the table. So I need to click over here in the table. Now when I go to menu, I get different options. So make sure you're in the table. And we want to edit table settings. Okay? Now, the first two are the only two we care about here in the table settings, where we start and then the table step. Well, usually want to start at what x is approaching, so I want to put that as a 2. Because we're interested in when x is 2. And my table step, I want something really small. Usually 4 zeros and a 1 is pretty good. In other words, we're kind of zooming in is what we're doing. We're getting in really close to 2. And then these you can leave on automatic and then hit OK. Now, you want to arrow up a couple so that you get 2 in the middle. Now, it is very clear, and again, I don't even care that at 2 we get 7. As far as the limit's concerned, that I am not interested in that at least. What I'm interested in are the y values here and here. And this would be the limit from the left, 6.99999, 6.9996. It's getting closer and closer to 7. From the right, I'd have to arrow down here 1 to be able to see a few more. And I think, come on. Oh, I got to do it. No, that's wrong. No. Let me see. There it is. Okay, I don't know why I had to hit that so many times. And there we go. So, and you're going to physically, on your worksheets and stuff today, you're going to physically write down those entries. Do 2 entries below 2, before 2, and do 2 entries after 2. Okay? And put down what the y values are. And that shows that the limit is 7. Because the y values from the left and the y values from the right are both approaching 7. Now, when we get to some of the more interesting ones, they'll be blank anyway. This is going to be undefined. You know, all those ones we get 0 over 0, this will be undefined. That's fine. We don't care about that entry. Still probably put it in our table. But you're going to actually copy down the table. All right. So all of those things lead us to believe, and this is a real simple example, but all of these things lead us to believe that the limit is 7. Whether it's a graph, whether it's direct substitution, or whether it was a table of values. Okay? And we need to understand all of those and when it's appropriate to use which one. All right. The second thing that can happen, and let's do one, we'll do one off of the worksheet today here in a second. But if you get one like limit as x approaches 3, x squared minus 9, x minus 3, when you do your direct substitution, what do you get?
0.
You get 0 over 0. Now, that's not an answer, that's not a number. That's undefined. But now, again, the words are important here. Functions are undefined. Expressions, mathematical expressions, can be undefined. Limits either exist or do not exist. So don't say that a limit is undefined. Okay? A limit exists or does not exist. An expression is defined or undefined. This is undefined. But the limit may still exist. Now here's where we go in and do our algebra. We're either going to factor, we're going to have to do a common denominator, or we're going to have to multiply by a conjugate. Those are the algebra things I expect you to be able to do. In this one, it's going to be factor, right? So we factor, we'll cancel an x minus 3, we end up with x plus 3, we go ahead and plug our 3 in, we get 6. There's our limit. This limit existed. Even though we originally got undefined, the limit existed. If we were to graph this, it would look like a line with a hole in it. Okay? Since we got the calculators out, might as well give that a try. All right? I would just come back into my table here, or I would leave the table up on the screen. I would just come back into here and delete this, so because we really don't need it anymore. Put in our x squared minus 9 and x minus 3. Now I'm showing you all of these different variations of this. It's not necessary for you to show all these different variations when you're doing a problem. It would have been just fine for you to do the factor, cancel, get 6. That would have been fine. Especially if it's a no calculator. You would not have to do the graph. Okay? If this was a calculator one and you graphed it. Now again, in my directions say show a table, show a graph. You know, you can graph it and just show the graph, I suppose, but it better be a really neatly drawn graph with the y values very specifically stated so we can see that it's approaching a certain number, okay? The table, a lot of times, is easier to do. The numbers are right there, just jot them down. So now, what do I need to change in my table? So I come over here to get to my table.
Where it starts at 3.
I need to start that at 3. So I go to my menu, my table settings, and I need to start this thing at 3 now instead of 2. And the nice thing is once you have that table step in there, it usually remembers it, so you don't have to adjust that usually again. But you do want that start that table at 3. Okay? And again, you see, we don't care that at 3 it's undefined. But it's very obvious from those numbers that to the left of 3, the seeing that many decimal places on your table?
Yeah.
Everybody is? Okay. All right, that's good. Because if you're not, then it rounds, and then you see all 6s there, and then that doesn't really do us any good. So that's what we would jot down. So again, evidence that the limit is 6, because the car on the left and the car on the right are both coming in towards 6. All right. So that's something that can happen. And we'll do another one. We'll do one on the worksheet here. The third thing that can happen to you is you have limit as x approaches 1. You've got x plus 3 over x minus 1. Right? Now you plug a 1 in there, you do your direct substitution as you're always supposed to, and what do you get? 4 over 0. That's also undefined, but that's a different type of undefined. 0 over 0 is a hole in the graph. The cars are still going to meet. 4 over 0 is a vertical asymptote on the graph, almost every time. So this particular graph at 1 is going to have a vertical asymptote, which usually means something to do with infinity. A vertical asymptote means the graph is coming up near that vertical asymptote, going up to positive or going to negative infinity. This is where you have more work to do. It is going to be true to say that the limit does not exist. Okay, that is the correct answer to this problem. The limit does not exist. The cars will not meet. But you have to go farther. You can never just stop by saying the limit does not exist. We have to say, what's the car on the left doing? That's the limit as x approaches 1 from the left. What's the car on the right doing? That's the limit as x approaches 1 from the right. That's what the plus means. Now the way you do that is you pick numbers to the left and to the right. Now if this was a calculator problem, okay, I'll show you in a second what this would look like. It'll be real easy because we can just see in the table what they are on the left and the right. Okay? But if it's a no calculator problem, then you have to manually plug in and see what the y values are. So what's something to the left of 1? 0.999. Okay? Something to the right of 1 is 1.0001, something like that. Okay? So what we have to do is we have to go plug these in. Now some people said, well, it's too hard to do in my head. Well, you don't really have to get an exact value. What you need is 0.999 plus 3. It doesn't matter. That's about 4. Matter of fact, I would just write 4. I mean, the top actually doesn't matter. What matters is when we get really close to 1, from the left, you get 0.999 minus 1. What's that? But it's a really, well, actually all I would probably write is small negative. That's all I'm going to write down there. What I have is 4 divided by a really small negative. What's that? A really big negative. 4 divided by a really small negative is a really big negative. Now, if the top would have been negative, of course, negative divided by negative makes it positive. It would have went to positive infinity. And that happens sometimes. Okay? Now, you put 1.001 into the problem, you get 4.0001. I don't care about all that. The 4 is really all that matters. It's just a number. And then 1.0001 minus 1 is going to be a really small positive. Positive 4 divided by a really small positive is a really big positive. So what I just said there, and now I know what this graph looks like. On the left of 1, it's going to negative infinity. On the right of 1, it's going to positive infinity. And I don't care about the rest of it because it only asks me as x approaches 1. So, limit does not exist. That means the cars didn't meet. Why didn't they meet? Because the one on the left was going down like this and the one on the right was going up like this. And it's all right there in my work. Now, in the video, they made an interesting point. They said in this particular function, 1 is the only place something bad happens. If I give you the same problem and say as x approaches 2, what would you have? Same problem, x approaches 2, you do your direct substitution, you get 5 over 1, the answer is 5, you'd be done. This one only has something kind of strange happening at 1, at the vertical asymptote. Okay, let's do the graph. Somebody got this graphed already? Surely somebody's got a graph already. You got a graph? Okay. You're the presenter. Nobody logged in?
I tried, but
It won't let us.
Oh. I wonder if that's because I didn't start. No, I started the class. I just didn't plug it in. Okay. Well, I'll go ahead and do it while you're doing that. So let's.
you are logged in as you read.
All right. So. All right, so we can see there where our asymptote is at 1. I need to go back and change my things. Oops, I wasn't on the table, so that was no good. Got to get into the table, go to the menu. Table settings, this time I need to start the table at 1. Okay, and here's what happens then when it's going to infinity. You just see some really big numbers in the thousands or 20,000. Depends how many decimal points I picked. If I would only went 0.001, these would have been numbers probably in the hundreds or something, okay? So it doesn't really, you don't really get that sense of going to infinity unless you get, that's why we did like 4 zeros and a 1. So it looks like on the left of 1, it's going to negative infinity. On the right of 1, it's going to positive infinity. Of course, we can see it pretty easily from the graph. That's one where if this was a calculator one, yes, you could do the table, but a graph would tell this story probably better or easier than a table even. If you have the vertical asymptote, if you can draw a decent graph, that could be a justification for your left and your right as well. Okay? And then the last thing I would say about these limits then is the ones from the book today. The pictures that you had in the book. And those are your piecewise functions. I mean, those are the other limits you have to be able to do, where again, the question you're asking yourself is, do the cars meet? And if they don't meet, then the limit does not exist. And you have to say, well, the limit on the left was this, and the limit on the right was this. Okay? If the cars do meet, then where do they meet? That's the limit. All right? So a piecewise function would be one where you're either looking at a graph, and some of you went ahead and did 41 and 42. We're going to do that as part of today's homework. The other thing I might do is not even just give you a graph. I might give you a piecewise function. You have to sketch it and see what it looks like. And so we'll talk about that one here a little later. All right. So that is it. I mean, that's really, if you can do that stuff with limits, you can do everything we need to do for the quiz when it comes to limits. Okay? Now, for some of you, the hardest thing might be the algebra parts right here. Okay? You might need more practice on that. I've got a worksheet here. I've just got an algebra worksheet with some practice on common denominator and conjugates if you want to take it. Okay? So that's up to you. All right, let's go through some on your worksheet here. I helped you with in class a little bit, didn't I? 2 or 3? Kind of both. 3 we looked at a little bit, I think. Again, when you do direct substitution on, one thing that was interesting about 3 is when you plugged in a 5, you first got 0 over 0, didn't you? You first got 0 over 0. Then when you did your factoring and canceling, you got like 8 over 0, right? And as soon as you got 8 over 0, that's what we were talking about over here, and that's when you had to check on both sides. Well, on this one, when you plugged in the first time, you get negative 2 over 0, right? Direct substitution. So you have to check to the left. So that's a does not exist. Not because it's undefined, but because it's a vertical asymptote. Okay, remember, 0 over 0 is undefined, and the limit still may exist. So we approach negative 1 from the left, and we approach negative 1 from the right. And so what did you get from the left of negative 1? How did this simplify down, by the way? Was that x? You ended up with x plus 2 over x plus 1, right? Okay. So, oh, did you get negative 2 over 0? Yeah, when you did your first direct substitution. Okay. Maybe you factored first and then tried to plug in. And then you get something else. You get 1. You get 1 over 0. Yeah, you get 1 over 0. But again, same thing. It doesn't really matter what you get there. All right. So now you get to this point, and so, okay, from the left of negative 1, that'd be like negative 1.0001, something like that. Well, if you do 2 plus negative 1, essentially, that's essentially 1. What we really care about is the bottom. Negative 1.001 plus 1 is a really small negative. So that's going to be negative infinity right there. From the right of negative 1.1, that's negative 0.9999. You add that to 2, that's essentially 1. And negative 0.999 plus 1 is a really small positive. So 1 divided by a small positive is positive infinity. So that's what your work needs to look like. If you're going to get full credit on this problem on the quiz, it's got to look like this. The answers does not exist, then you got to have those two pieces. All right. Number 4, what happened on number 4? Direct substitution work on that one? That was the one where it just worked, right? You plug in a number, you just get an answer, and you're done. Okay? Let's talk about number 5. This is the conjugate. We're looking at the conjugate method. That means you take radical x plus 3, and you take radical x plus 3. And you FOIL. Now you don't FOIL out the top. You leave the top alone. The bottom FOILs into what?
X minus 9.
X minus 9. Now there's a little bit of a trick here before you cancel. What do you got to do? You have to take out a negative on either the top or the bottom. It doesn't matter. If I take a negative out of 9 minus x, it becomes negative 9 plus x, which of course is the same as x minus 9. So I just took out a negative. Now that cancels that. And now I can plug in my 9 for x. And I kind of skimmed over the fact when we first plugged in, we got 0 over 0. Okay? So now I plug in my 9. I get square root of 9 is 3. 3 plus 3 is 6. Don't forget I got that negative over there. Final answer, negative 6. All right. On this one, I've got a radical minus a radical. So I'm going to have to do radical plus a radical up here. Okay? Now again, the radical is x squared plus 12. And then this one's 12. I don't even care. Those don't change. So the key thing, though, is I got radical minus a radical, so I'm going to do radical plus radical. Top, I just leave that alone. The bottom, when I FOIL that, the first times the first, the square root's gone. I get x squared plus 12. Outers and inners would drop out. That's the whole point of doing the conjugate. Square root of 12 times square root of 12 is 12, and it's a minus. So the beauty of that is the 12's disappear. Leaves me x squared there. The top had an x squared and then this whole big mess. But since the 12's disappeared, now the x squareds can cancel. And so all I'm left with is my radical x squared plus 12 plus root 12. Now I can put in my 0 for x. Put in a 0 for x, I get radical 12 plus radical 12, which is 2 radical 12. Mrs. Andreessen would just shudder if you left your answer like that. But it's okay. It's okay for this class. Why do you even learn it? What would it be? 8 radical 3? 4 radical 3. 4 radical 3. See, that's why I don't make you do it, because I didn't know. 4 radical 3. Okay, and some of you it might bother you. It used to bother me too, and I've gotten over it. All right, 4 radical 3 is fine as well. Okay, common denominators or bow tie, whatever you want to call it. Okay. Now, the common denominator is just those two multiplied together. Now, on this algebra worksheet I give you, sometimes you can have common factors. It's kind of like if I gave you and asked you the common denominator between 1/4 and 1/8. Well, it's a common denominator would be 32, right? 4 times 8. But it's not the least common denominator. Now, actually, it doesn't matter. When we're doing these problems, I don't care if you get the least common denominator or not. If you don't get the least common denominator, it just means it'll reduce when you get done. You have something extra that will cancel, but it still works. Okay? So when you're getting into these problems, it's kind of like, what's the common denominator between x squared and x cubed? X cubed. And all you'd have to do is take this one times an x and an x. But if you want to have the common denominator be x to the 5th, you can. You would take this one times an x cubed, top, bottom, and you take this one times an x squared, top, bottom. Right? And make x to the 5th your common denominator. It's perfectly fine. When you get done at the end, you'll cancel. So if you do take that algebra worksheet, it does actually get into some that are more complex than we even have to mess with. But here I would just take this times this. So this fraction is going to need a 5 plus x. And this fraction over here is going to need a 5 minus x, top and bottom. And that'll give me my common denominator of 5 minus x, 5 plus x. And I would not even FOIL those out. Okay? Now on top, if there were some things other than 1, we'd have to distribute them and so forth here because we're trying to gather terms together, hoping things disappear. But since they're just 1s, we end up with 5 minus x. Don't forget this minus sign in the middle here. That's one that will get you. Minus, and then 5 plus x. So we're going to have to distribute that minus. And I won't forget about that 3 over x out there. That'll come in a minute. So we end up with 5 minus x minus 5 minus x when I distribute that. So what happens? 5's cancel. We end up with negative 2x. And then our common denominator. 5 minus x, 5 plus x. So there's the algebra stuff you got to be able to do. Now there's still that 3 over x outside here, but that's going to let us cancel the x's now. And of course that's the key thing because, and again I skipped over the direct substitution. When you tried direct substitution, this one, well this was interesting. When you did your direct substitution, you got 3 over 0 times 0, right? What's 3 over 0 times 0? It's really 0 over 0. Right? Now you might say, well, wait a minute, I thought anytime you multiply by 0, you get 0. Well, that's not true. Anytime you multiply a number times 0, you get 0. But 3 over 0 is not a number. It's undefined. Okay? So 3 over 0 times 0 is this. Okay? In chapter 4, we'll get into this a little more. Okay? What this really is 3 over 0 is that vertical asymptote thing we talked about. What this really is a fraction that's going towards infinity times a number that's going towards 0. Right? That's what's really going on there. We'll do this a lot more in chapter 4. Well, what's that going to be? A number, because what happens when you multiply something by a number that's getting bigger and bigger and bigger? What happens? Just take a number, take a constant, times a number that's, and let that second number get bigger and bigger and bigger. What happens to the product? It gets bigger and bigger and bigger. What happens if you take a constant, multiply by a number getting smaller and smaller and smaller? Gets smaller, smaller, smaller. So the question here is, what happens when you take a number that's getting bigger and bigger and bigger and multiply it by a number that's getting smaller and smaller and smaller?
It gets smaller and smaller and smaller.
Or smigger and smigger and smigger.
Yeah.
It depends on whether the one getting bigger is getting bigger faster than the one getting smaller is getting smaller. It depends on their rates. What's a rate? What's a rate of change? Derivative. Derivative. The answer to this question depends on derivatives. Okay, there you go. There's another reason we need calculus. See, a question you didn't even know you needed answered. All right. Anyway, for us right now, we'll just say it's undefined. Okay? For us right now, we just say it's undefined. It's 0 divided by 0 at this point. Okay? So, anyway, 0 over 0, we keep going. We do our common denominators. We get to this point. The x's will cancel. Now we can put in our 0. So we get 5 minus 0, 5 plus 0, so that's 25. Multiply the tops across, we get negative 6 over 25. And there it is. There's the final answer. Okay? On this one, you put in your 0, you get 0 over 0. Here, your only option is to FOIL that out. If you want to do Pascal's triangle, we talked about the other day, make it a little quicker. Otherwise, you pretty much just have to FOIL it out. So you'd have, if you do it that way, you'd have 4 plus 4x plus x squared. And then times a 2 plus x, so that's 8 plus 8x plus 2x squared plus 4x plus 4x squared plus x cubed and minus an 8. So the 8's drop out, which is nice. We end up with 12x plus 6x squared plus x cubed all over x. We can take out an x. Do it the quick way. Take out an x, we get 12 plus 6x plus x squared. Now as x approaches 0, that goes to 0, that goes to 0, and we just get 12. Okay, so FOIL it all out, see what happens, do some factoring. All right, so there's some practice on all of the 3 different things that can happen with the algebra. All right, now I don't have a picture to put up here of this one in the book, so I'll just try to draw it real quick. I thought I had a copy of this. I'll resent that. All right. So what do we got here?
Yeah.
What? All right.
What? How come you don't want
Here we go. So, starting with number 13, these are the really important ones I wanted to discuss here. On 13, as x approaches 0, what is the limit? 2. The y value is 2. As x approaches 0, the cars are coming in, and they meet at They meet at 2. Okay, as x approaches -3. Right over here, here's -3. What's the limit? -1. We do not care about this dot up here at -1. Now, what do they call this function? F? F of -1, and I may ask you questions like this on the quiz. F of -1, you would write what? 1. But the limit as x approaches -1, which is, or excuse me, not -1, I'm sorry, -3. F of -3 is 1. But the limit on number 14 as x approaches -3 is -1. It's where the cars are approaching, -1. Okay, 15, as x approaches -1, we got what? This is, okay, this is important. Listen up now, please. On number 15, and the back of the book probably did this differently than I want you to answer this. On 15, don't say undefined. That's not the right term. Does not exist. The limit as x approaches -1 does not exist, but you can't stop there. You cannot stop there. Ever, ever. When you do a limit problem, you cannot stop with does not exist. You have to look at each side. The reason it does not exist is the cars don't meet. Why don't the cars meet? Because the one on the left comes somewhere different than the one on the right. So you have to say the limit as x approaches -1 from the left is 1. And because this car is coming right in here at 1. And the car on the right is coming in up here at 2. So the limit from the left is -1, or excuse me, is 1. The limit from the right is 2. You have to write that down. Okay? Limit does not exist because the cars don't meet. Number 16, the limit as x approaches 2 from the left is 1. As x, number 17, as x approaches 2 from the right, right here. So from the left, it's approaching 1. From the right, it's approaching 1. Whoops, I forgot my dot down here. Number 18, the limit then as x approaches 2 is 1. In other words, what they did with those 3 problems was they said, okay, the car on the left's approaching 1, the car on the right's approaching 1, so therefore the limit at 2 is 1. Because the cars from both sides are approaching the same thing. We don't care about that point. Doesn't mean a thing as far as limit goes. Okay, number 19, -2 from the left is approaching 0. That's this point right here where it's crossing. As you can clearly tell, that's -2 on my graph. Number 20, as x approaches 1 from the right, that is 0. And number 21, as x approaches -4 from the right, that's down here. Okay, there is no left, so we wouldn't be able to even ask that question. You would say does not exist because it's not on the graph. Number 22, as x approaches 4 from the left, that's this point down here, which is -1. Number 23, as x approaches 3, where's that point? That's this right here. Oh, that's f prime. Time out, time out. There you go. Okay. As x approaches 3 from of f prime. So now f prime is what? The slopes. So now all we have to say, well, number one, you could draw an f prime graph if you want to look at those y values, but you can just say to yourself, what are the slopes? Well, as we come in from the left, what are the slopes? And they're not changing, are they? So the slopes are -1, -1, -1. If we were going to graph that, wouldn't it just be down here at -1, horizontal line? So from the left of 3 and the right of 3, the slopes are going to be -1. Right? Here would be 3 right here. So from the left, from the right, -1. So that's the answer to that. Okay? As we approach -1 from the right. -1 from the right. What are the slopes? 0. And they're constant. So they're not only approaching 0, they are 0. 25, -1 from the left. What's this slope? 1? Slope is 1. So from the left, the slopes are 1. So then well, they didn't ask it, but we just did -1 from the right, the slope was 0. -1 from the left, the slope was 1. What's the limit of f prime as x approaches -1? Does not exist. Because we just said that the slopes on the right were one thing, the slopes on the left were another thing. So on the graph of f prime, they would not meet. The slopes are approaching different things. Okay? So the limit would not exist. All right, then they asked about f prime -3. As x approaches -3, still 1. The slope of this is 1 the whole time. So from the left, the slopes are 1. From the right, the slopes are 1. Okay? So a little different twist on that, throwing in the derivative there. And again, you could have graphed f prime if you wanted to help you with that, or you could just think about those slopes. All right, so that's really the fourth piece of what we had up here on the board earlier with the piecewise functions, because that's clearly a piecewise function, right? I mean, that's just kind of a made-up graph of a bunch of different pieces, okay? And so we could do limits with those. Okay, let's take a look at this video then from all right, let's see if this is ready.
Now you have some idea
So
of
good,
what
I
a
want
limit
to
is,
see it again.
and we need to talk about when does a limit exist.
My school math
To
teacher showed
illustrate
us a
my
limit
point
video
before we get
7
started,
times.
let's set up an example.
And it wasn't
Let's say
as exciting
you and
as
a
this
friend are going to meet for dinner, and you're meeting at a diner that's centrally located between the two of you. If you live east of the diner, and your friend lives west of the diner, and you both want to drive to meet there, ideally, the roads which lead to the diner will lead you to the same place. If you travel towards the diner from the right, or east, and they travel towards the diner from the left, you should meet up in the same place. Mathematically, this is basically what a limit is. A limit exists if you travel along a function from the left side and from the right side towards some specific value of x. as long as that function meets in the middle, as long as you arrive at the diner, as long as the heights from the right and the left are the same, then the limit exists. Now it's time to get down to the brass tacks and look at this mathematically. Take a look at the graph of this function f of x. Visually, you can see that it's got a break in it at x equals 4. So, if we travel towards 4 from the right, we will arrive at a height of 2. However, if you travel towards 4 from the left, you will arrive at a height of 1. This means that no limit exists for f at x equals 4. Let's go back to our diner metaphor for just a second. Notice that as I'm traveling along the road from the right, I end up at a height of 2. But if you travel along the road from the left, you end up at a height of 1. These heights don't match. We won't both arrive at the diner, and no limit exists. We call the height at which we arrive from the right the right-hand limit of f of x, as x approaches 4 from the right. And we denote this with a little plus sign in our limit symbol. Our height that we arrive at from the left is called the left-hand limit of f of x, as x approaches 4, and it is denoted with a little negative symbol. Mathematically, in order for a limit to exist, both the right and the left-hand limits must be equal. Now let's change this function just a little bit. This new function, we'll call g of x, does possess a limit. Can you see why that's the case? It's because the function no longer has a break at 4. Now, there's something to be said here. The previous function did not have a limit at 4. It did have a limit at many other points. For example, a limit existed at 1, at 2, at 5, at 0. All these x values showed locations where the graph did not break. In essence, a graph will not possess a limit if it breaks at the given x value. That's why our new function does possess a limit at x equals 4. Now, let's go back to our diner example one last time. Let's say we're traveling towards the diner. We both arrive at the same location, but the diner isn't there. Maybe it's caught fire or something. Does that mean the limit doesn't exist? The truth is, the limit will exist even if the diner's not there, because you still arrive at the same place. In other words, mathematically, a limit can still exist if your destination is a hole in the graph, because it doesn't matter whether or not the point is actually there. What matters is that you arrived at that point, coming from the right side and the left side. In conclusion, a limit exists on a graph if you arrive at the same height coming from both the right and the left side of the given x value.
Wait, one more time. All right, this is some new stuff now on this one.
Calculus relies heavily upon the existence of what's called continuous functions. In fact, most of your important theorems include a prerequisite that any function in question must be continuous before you could even think about applying the theorem. For example, the intermediate value theorem, which we'll also learn in this chapter, requires that the function be continuous. Well, in theory, continuous functions are predictable functions. They have no undefined points, no breaks, no holes, no jumps in the graph. But enough talk. Let's take a look at some pretty pictures. Now this function f is continuous, but these, g, h, and I, they're not continuous. Each of them, in fact, is discontinuous for a different reason at the x value of x equals c. See, now this one, on g, you've got a little hole in the graph. That's called point discontinuity. Over here, on h, you've got a vertical asymptote that breaks the graph. Now this is called infinite discontinuity. And finally, here on graph I, you've got a graph that just plain snaps in the middle. And that's called jump discontinuity. Now how can you judge just by looking at the graph of a function if it's continuous or not? Well, a continuous function makes a good bridge. Now see, if I drive across the graph of f, it holds up nicely. Whereas if I try to drive across the graphs of the other function, I'm either going to fall through or fall off.
More fire. All right, So
Sweet.
we've talked already about continuous functions being nice and smooth, and you don't have to lift your pencil, that kind of thing. But we're going to talk about a more formal definition of continuity, and you're going to have to be able to apply that definition. In other words, one of the questions on the quiz is going to be for a particular function, whether it's one I have you graph on your calculator, or it's a graph I give you, or maybe it's a piecewise function I give you, you have to sketch. I'm going to ask you, where is this function discontinuous? Where is it not continuous? And then you'll have to give the reason why it's discontinuous at those points. Not informally, but in the formal definition. In other words, don't say, well, there's a hole there. There's a vertical asymptote there. There's a break. Okay, those are the informal reasons why it's discontinuous. We want to get into the more formal, so that's coming up.
So, continuous functions are predictable. But what does that mean? Well, it means two big things. One, no breaks. Well, we already know that breaks occur in functions when no limit exists there. Therefore, for a function to be continuous, it must have a limit at every x in its domain. Secondly, no holes. Continuous functions must be defined everywhere in their domain. Mathematically now, we say that continuous functions have this property. For every x equals c in their domain, the limit as x approaches c of f of x is equal to f of c. In other words, not only does the limit exist at every point, but the height the function reaches for every x matches the limit. How can you tell if this happens? It seems pretty complicated. It's actually easy. If you can evaluate any limit on f of x using only the substitution method, then the function is continuous. And that's all there is to it.
Okay? All right, so let's write this down more formally.
What?
I think we're okay.
Mad at you.
All right.
That's really messed up. Looks like a German word. That made it worse.
Made it work. Okay. Huh. All right. A function is continuous at x equals a if, and we're going to break that into three things. Now, they kind of summarized it in one statement, but that one statement really is dependent on two other things. So, for a total of three. In other words, they said that the limit as x approaches c of f of x has to equal f of c. So, we'll write that down as our third of the three options. Okay, so the third one is the limit as x approaches, we'll use a, they use c, but I think our book uses a. Alright, so that's what they said had to be true if a function was going to be continuous at point A. Now, when we say a function is everywhere continuous, means it's continuous at all of its different points A, all the different points, right? Like most functions are continuous most of the time, they just have 1 or 2 or 3 points of discontinuity. For a function to be continuous, there can't be any points of discontinuity. So if you just find one point where it's not continuous, then the function is not continuous as a whole. Okay? Still can be continuous at various points. Well, if the limit, which is a number, is going to be equal to the output at A, which is a number, then both of those numbers must exist, right? So the first thing that has to happen, or actually there's no necessarily order here, but I'm going to put f of A must be defined. And again, we've got to use the proper language. We're talking about the output at A, so that is defined or undefined. When you plug a number into a function, you either get out an output or there is no output. Like if you were looking at a table of values, there was no output for that, it's undefined. Okay? Or 1 over x, you put in a 0, it's undefined. You don't get an answer out. So for this third one to be true, then there must be an f of a for it to be equal to. So f of a must be defined. There must be an output there. And then the limit as x approaches a of f of x must exist. And again, notice what we said. We talked about f of a must be defined. We talked about the limit must exist. There must be a limit at that point. And then what the third one then says is, okay, if you've got an output and you've got a limit, then the two have to be the same. They have to be equal. If you have all those things and all the points, then the function's continuous. So this is the more formal definition of continuous. This is what I'm going to want you to reference. So let's take a look at the examples that violate one of these three. All right? F of a must be defined. Well, one example would be the one I was just mentioning, f of x. There's no output at 0. Right? There's no output at 0. So this function is discontinuous at x equals 0 because there's no output there. All right? What would be another one where there's no output? A hole in the graph. So if I've got a parabola except it's got a hole right there, that limit, this would be point A on this one, this would be point A on this one, okay? This is not continuous. You'd have to lift your pencil, right? You'd have to, the car would fall through the hole, right? As it was driving along. The limit exists on this one, right? It's wherever that hole is, but it's discontinuous. You have to lift your pencil or whatever. But the reason is because the function is undefined there. All right. Those are probably the two main ones. So these are both discontinuous because they violate number 1. Number 2, we could use 1 over x as an example for that one. Does the limit exist at 0? Do the cars meet? No. One car is going up to positive infinity, one's going to negative infinity. So this one, 1 over x, actually violates both 1 and 2. There's no output at 0, and the function, or the limit, doesn't exist either. Okay? Piecewise functions are bad about this one. Okay? A lot of times you get a piecewise function that does something, like that. The limit doesn't, it's not continuous. You'd have to lift your pencil. There's a break. I like what they said earlier about a discontinuous function. Any graph that's got a break or a hole or a jump or something weird going on that's just not nice and smooth, that's discontinuous. All right, so this one, the limit does exist. The cars don't meet. All right, and this one, to violate this one, it's possible. I mean, think of a situation where these two both are true. Both of these happen, but this one doesn't happen. We had it on our homework today. Yeah, it's just like this piecewise function up here where you have a hole and then you've got another point defined there at A. Okay? The limit exists because the cars would meet at the hole where the diner used to be. The function is defined at A. It has an output. The output's right here. But they're not equal. Where the cars meet is not the same as what the output is. So f of A does not equal the limit as x approaches A. All right, so that one would violate the third one. So you really need all three of those to kind of think about the different types of discontinuities. They called this one a jump discontinuity. They called this one an infinite discontinuity. They called this one a point discontinuity. We don't have to remember those terms necessarily. But I do want you to use this. So if I give you a picture like this and say, where is this discontinuous? And say that was 0.7 or something at 7, okay? So you'd say, well, it's discontinuous at x equals 7. And I would say, why is it discontinuous? And you'd say, because the limit exists and the output exists, but they're not equal. Somehow you'd have to say that it violates this one. Okay? If I give you a picture like this and ask you where is it discontinuous, of course, that's the easy part, identifying where it's discontinuous. Why is that discontinuous? And don't say because you have to lift your pencil. Don't say because it breaks. you say because the limit doesn't exist there. Okay? If I give you one with a hole in it and say, where's it discontinuous? You tell me, why is it discontinuous? You say, don't say because there's a hole there. Say because the function's not defined at that point. Okay? So those three reasons we want to know about. Okay. Let's see what's next here. All right. That's pretty much all of the new information I have. I'll work a couple of these with you. There are things we've done before. The first side with the calculator limits we just did earlier today. This is where we were doing the table. I was doing the table stuff, so maybe I'll just work one of those together with you. And then the ones on the back, there are some on the back, and these are also to be done with a calculator, but these are like ones we had in our homework. I think it was number 34 and 35 a couple days ago. And we'll turn that over and do one of those as well. I think we got time to do one of each of those. So, thank you. All right. So, all right, looking at this one here. What is that?
Okay. How about that? Check this out.
All right. So, evaluate the following limit using your calculator. If the limit does not exist, check the one-sided limits. That goes without saying, but I said it anyway. If it doesn't exist, check the one-sided limit. So you get your calculator out, and we go ahead and we type this in. All right, so we go up here, and we're going to type in square root. So you need to be able to do both here, both the no calculator ones like we had for today, and then these ones using your calculator. And on the quiz, this would be one where I would probably, very likely, just tell you what the answer is. I would give you the limit statement and then say equals, whatever. And then my directions, instead of find the limit, would be to justify the limit. All right, so we go ahead and we type that in. And where do we want our table? Click on the table. We want our table to start at 0. Now, as I looked at this worksheet, after I made this up, I looked at the worksheet and I looked at all the limits on the front and the back, and almost every one of them, x approaches 0. So, which is nice. You don't hardly have to change your table at all. That'll be good for you. But I don't want you to think that every time you do a limit that it should start at 0, that you're always looking at 0. It's whatever x is approaching. Whether it's 2 or 1 or 3, whatever, that's where your table should start. Okay? So we start our table there. Garrett, were you here for this?
No.
When we did the table? Okay. So over here, now, of course, remember, it's going to use scientific notation. Is that what you're getting?
No, because
What'd I do wrong?
enter when you do that your graph. So.
Thank you. So I got... All right. So, is okay, Josie, you're the presenter. So I don't have to go type mine in. All right. So, Josie's got the equation typed in here. Notice there's nothing past -1 on this function, and there shouldn't be, because if you look at the square root of x plus 1, if you put anything left of -1, like -2, you get negative under the radical, and it's all undefined over there. But that's okay. We only care about this point right in here. We only care about as x is approaching 0, what is that approaching? And clearly from our table, we can tell it looks like it's approaching -1, or no, +1/2. +1/2, is that what you're seeing? Okay, So on your worksheet, and please, oh, whoops. Sorry. I mean to show off everybody's grades. All right. So what you should have on your paper, and what I'll be looking for is you've got -1/2 or -0.5 as your limit. And again, on the quiz, I may just have this limit equals -1/2, and you're supposed to justify it. So, or geez, why did people make that? +1/2. And so then, I would say make a table with 5 entries, because that'll show you 2 on each side. You got 0. Now this was, something like this. Don't put that scientific notation stuff that they had, whatever. Put, something like this. Not so concerned with the left side, really. But just to the left of 0, just to the right. And over here you had, what was it, was it 499 on this side?
No.
What was to the left of 0?
5.
That was 5, is a little over 0.005, right?
3.
0.501, and this was undefined. You don't even have to put anything there. And then on this side it was 0.4999, 0.4999. This table shows that yes, the limit is 1/2. That the car on the left is coming in from above 0.5, the car on the right is coming in a little below 0.5, but it doesn't really matter, they're meeting at 0.5, and so that's what I want to see on your paper. Now you could sketch the graph as well, but that's a little harder to show that it's 0.5, because then you have to kind of trace and show some points. You can't just draw a graph and about between 0 and 1 and here it comes in. I want to see specific. And so the table really does that probably easier. And once you have the table up there, it's just pretty quick to be able to sketch it. Okay, that's that side of the worksheet. Let's flip over to the second side. And now we want to come back and connect this to what we were doing with derivatives. The whole reason we got into limits here was because the derivative formula. Every one of the limits on this side, and this was, you probably remember this hopefully from homework a few days ago. This limit right here represents a function f and some point A, because all the limits on this page look like the limit as h approaches 0 of f of a plus h minus f of a all over h. They all look like this. And remember, where did this come from? What's this part of it in red here? What's this part? Let's shift gears a little bit here. That's the slope between 2 points. And what's the green thing do? 2 points become 1 point. Okay, so this is all about slope, and this is derivative. But now, when we come to work this problem, now we switch gears again. Now we're thinking, okay, I got to solve this limit problem. How do I solve this limit problem? Well, here's how you solve limit problems, right over here. Right? We did some with algebra. We did a bunch the long way, we called it, which was basically solving limits with algebra. On this page, I'm going to let you use your calculator to solve. Okay? But first, what function is this? Well, we said to look here at this a plus h part. Here's my a plus h right there. The a plus h goes in where the x was. So what must my function have been? My function must have been 2 to the x power. My a must be 3. And of course the 8, that makes sense because the 8 would be 2 to the 3rd power, right? That's f of a. So that's 2 to the 3rd, that'd be 8. So that makes sense. So what this limit is finding, now on this side then we're really kind of doing 2 things at once. What we're about to do is type this into our calculator to do the limit, and when we get an answer out, that number is not only going to be the limit, but it's going to be what? it'll be the slope of this function 2 to the x at 3. Now see how we got to be careful here. Not at 0. Yeah, the limit is h approaches 0, and when we put in our calculator here in a minute, we're going to be interested in 0. That's right. But for the derivative piece of it, it's at the a value. So the slope of 2 to the x at x equals 3. Okay, we're going to test this. Oh, I got just enough time. All right, so we're going to go to our calculator, and we're going to put this part in green. Oh, I got 2 greens. That's confusing. We're going to put this part in the big green circle into our calculator. But we can't put in h, so we're going to put in what?
X.
We're going to put in x. Okay, so we go back to our calculator. And let's graph it. We got to graph it. We got to graph it. Josie, we got to graph it. There you go. Anybody else got it graphed yet? It's okay. I'm going to see if I can beat you. You got it? Okay? No. So what are we going to type in? On the top, we're going to type 2 raised to the 3 plus x. We can't use h in a graph. Okay? Arrow. And then I'm going to do minus 8. And on the bottom, I'm going to put what? X. I can't put h. And I'm going to hit enter this time. And I'm going to graph it. Now, where do I care about on my table? Now, careful. What is my limit? As h, we're not using h now, we're using x. As x approaches 0, right? The 3 was something different. All right? So my table's good. 5.545 something it looks like on both sides. Would you agree? So this limit is 5.545. Now I'm going to want you to write that table down. Okay, because it said evaluate on your calculator, so I'm going to want you to write that table down on the worksheet. And what did we say it was? Remember, 3 decimal places. So we said it was 5.545, right? Now, I just want to check that second meaning of what we just said. We said that is the slope of 2 to the x at x equals 3. Now I'm going to do that for you real quick here on my calculator screen here. Don't worry about doing this part. I'm going to go ahead and I want to do the derivative of 2 to the x. Just yell at me. I'm going to do the derivative of 2 to the x, and I'm going to go outside of it. I'm going to put my vertical bar with x equals 3. So I'm going to do the derivative of this at 3. I'm going to hit Control Enter so I get a decimal. Please, 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 please work. Please work. Yes. 5.545. You think I'm joking? I had done this ahead of time, so I really was. See, there you go. By doing that limit, which was a totally different function than 2 to the x, right? By doing that limit as an x approached 0, that y value has like a double meaning. Okay? Because the limit was a special looking limit that fit our definition, it was that. All right. So, for tomorrow, do both sides of this worksheet. Okay? And on 2.3, now these don't take very long. This is that picture, that graph, but I want you to practice these. 27 through 36 and 39 through 42. But, okay, that's the one where the limit is x approaches 1, you look at the graph, boom, you write down a number, okay? It's looking on them from the graph. So those are pretty, I think people found it pretty easy. But both sides of the worksheet, and then those problems in section 2.3.
But then,
What's that? Oh, and on your way out today, there's one side of this worksheet is some conjugate and some radical algebra stuff, and then there's some common denominator fraction practice on this side. Okay, it's just kind of something I threw together. So,
no, that's what I think you need that.
extra credit? No.
Why not? Why not just like one extra credit? Or
No.
10 points. Fine.
We'll have some extra credit, but you're going to have to do more. It'll be more interesting than that.
More
I
interesting.
don't want it to be interesting.
More interesting than that.
Dull, boring, easy. You can see your phone. Right. I have so many things coming to me in the middle.
Hey, I get a new phone in December. Okay, I don't need your fake excitement for me, okay? But no, it's gonna be like, what's it called? The LG Enlighten.